Hello, my name is Huan Liu, and I'll talk about our work in the 2022 Orbit Challenge. This is a joint work with Li Gu, Zhi Xiangchi, Yang Wang, and Yuan Haoyu. Here is the overview of our proposed method. For producing discriminative prototype, we first follow fit to meta-learn a transformer encoder block on top of feature extractor. Then, during personalization stage, given a support video sequence, we propose a uniform clip sampler to sample frames uniformly from each video. Sampled frames are then used to form support clips. In order to identify and remove noisy support frames, we apply canny edge detection, and based on the detected edge to determine if a frame should contribute to prototype. All valid frames are then sent to fit to calculate the prototype for each class. After that, we predict the class of each frame using the prototype by solving nearest neighbor. I will introduce each our used technique. To recognize object in few-shot manner, a powerful backbone network is required to produce discriminative features for calculating prototype, especially when frames from the same user have similar background. To improve on the current backbone, we follow fit to add a transformer for embedding adaptation. A visualization of adapted results is shown on the right-hand side, from which we can observe that the adapted prototype is closer to the center of support frames. Current random sampler cannot guarantee the sampled frame can cover all useful information across the whole video. Another issue is that the random sampler usually samples long video with low sampling rate, but samples short video with high sampling rate. This is not intuitively correct. To address the issue, we propose a uniform sampler. It uniformly samples frames across the video and maintains same sampling rate agnostic to the length of video. Our observation shows that many frames in support set are noisy and do not contain target objects. Such frames should intuitively do not contribute to the calculation of prototype. To identify invalid frames, we propose to use canny detector and remove the frames without extensive edges presented. Besides our novel algorithm design, we also make contributions from the code quality perspective. We deeply investigate the implementation in the original Orbit codebase and reflect the data pipeline of episodic learning to encourage modularity, compatibility, and high performance. Firstly, in the original codebase, the logic of episodic learning is implemented with a stack of functions in a deep class. To encourage modules to be reusable and replaceable, we decouple them from that deep class into multiple independent shallow classes. For example, with a low coupling codebase, users can try different sampling strategies without modifying the rest of the modules. Secondly, we make some modifications to API and encourage the codebase to be more compatible with other domain-specific libraries in PyTorch ecosystem. As a result, users can directly use highly optimized data augmentation modules in Torch Vision to process Orbit data. Also, users can easily follow the common practice in standard supervised learning. Lastly, we try to accelerate experiments. To be specific, we find the GPU utility cannot maintain at 100%, which indicates the data preparation can be a bottleneck. So, we introduce multi-threading to hide the latency of loading frames from the disk in each episode. The performance benchmark is shown in the following tables. The table on the top shows the performance benchmark on the training data pipeline. We calculate the average time of preparing 100 episodes in the training set. It demonstrates that our re-implemented data pipeline with multiple CPU threads and CPU workers can be 2.7 times faster than the original codebase. The table on the bottom is benchmarking testing. We calculate the total time of loading all video frames in the test set, including 300 videos from 17 users. Our re-implementation can also accelerate the testing speed. Here are the quantitative results. From the table, we can observe that our method with the introduced three techniques performs best. We finally show the improvements of each user. By checking throughout the figure, it is noticeable that our method can improve the recognition accuracy for most of the users. Thank you for listening.